All right, we're going to take a look at a mathematical analysis of motion now. We're going to take it from the perspective of what we know about graphical analysis. And we're going to use it to analyze motion moving on the x-axis or horizontally. The equations that we already know that we'll use, they're considered usually five, either the big five or five kinematics equations. Some people use the big three, but the first of the five would be derived from the displacement time graph, and that is that velocity is equal to displacement over time. Remember, it can also be average velocity equals distance over time. The second, from the velocity time graph, if you are changing your velocity, you are accelerating. And from this relationship, we get the slope of a VT graph is your acceleration. And that can also be looked at in terms of final velocity. Another of our kinematics equations comes from a cheat that we use in graphical analysis to make changing values on a graph easier to analyze. You can cheat them and make it look like just one value if you can take an average. So this might be important, for instance, calculating the displacement. We know displacement is the area under a velocity time graph, and with changing values here, you can simplify that mathematical calculation by taking the average value and just looking at the area enclosed there. That really is just displacement equals velocity times time from v equals d over t. But mathematically what you're doing here is you're taking the first velocity and you're adding it to the second velocity. And you're dividing that by 2 to determine its average. In this case, between 10 and 20 would be an average of 15. And then you're multiplying that times time, and that is giving you a displacement x. All right, our next equation comes from the combination of the previous two. If you look at the definition of acceleration, and if you look at the cheat to make a changing velocity and average velocity, then calculate its displacement, you can solve this equation for t and substitute it here. You end up with the change in velocity over acceleration. The 2 and the 8 come up to this side, and you FOIL these, and you might be able to just look at those to figure out that you're going to end up with v2 squared minus v1 squared. And then rearranging that for how it's shown in most data booklets, you end up with final velocity squared equals initial velocity plus 2 times acceleration times displacement. So the last of the equations that we're looking at come from an analysis of a parabola. If you look at an xt graph, if you take an object and shoot it from elbow level, you end up with a parabola that looks like that. The standard form of a parabola gives you that when the y value equals 0, all this stuff is true. Well, a 0 y value is basically your initial position. And this c value, which is the y-intercept, is your change in your initial position. So if you bring the c over here, you end up with a change in position, and that's really your displacement. What we know are the x's here, they're really t's, and so you can rewrite this like this. A t squared plus bt. Now, if there is no acceleration, this part of the equation disappears. And we know that displacement is equal to something times time. Well, from velocity equals distance over time, we know that distance is equal to velocity times time. And so this really is representative of a velocity. And then we know from parabolas that the larger the coefficient a is, the more wide or open your parabola is. And so if we shot something here on Earth, it might look like this, but if you go to Saturn and shoot something, it might look like that. And basically what that's doing is it's closing the parabola, and we're using that example to justify that as you increase this value of the coefficient here, that's representative of a change in the Earth's gravitational acceleration. And so really, this coefficient in front is representative of to acceleration. Now, without the calculus, it's hard to show that this actually needs to be your acceleration divided by 2. But from this right here, we can write out the next of the kinematics equations. You have your displacement equal to your initial velocity times time plus 1/2 of acceleration times squared. And that right there is the last of the five main kinematics equations that we use to mathematically analyze motion. All right, so here they are, the kinematics equations. We've got the slope of a dt graph. We've got definition of acceleration from a vt graph. We have the cheat where you average the velocities out to make them one velocity and multiply by its time to get you displacement. We have some math from parabolic trajectories, and then we have change of velocity with respect to acceleration and displacement. If you are looking at resources from across the globe, like a lot of teachers are providing, you've got to be able to freestyle with another form of these kinematics equations too. So this one's a little bit across the pond biased. Displacement really in the IB curriculum is an S, and oftentimes we sort of just choose to use X because we're working on the X-axis. Initial velocity is given the symbol or variable u, and so you get a different version of all of these equations. Looks like we're missing one. There they all are in IB form. All right, problem solving with these kinematics equations really is just 8th grade algebra. Sometimes it can be difficult when there's multi-step problem solving involved. What I coach my students to do is to identify the variables you've been given and then look over at the equation list, remembering those variables, and just find the equation with the variables that you're looking for. Problem solving wise, it's always the same. Each of the kinematics equations pretty much has exactly 4 variables, and so all you have to do is identify 3 variables and then figure out the variable you're looking for and go right to the equation list and find the right equation. And so an example of that here, we've got a car that goes from 10 to 0 to a stop sign, and in that time covers a total of 20 meters. And first question would be, what is the acceleration? And so I ask myself, 2 V's, an X, and an A, and I go to the list, 2 V's, an X, and an A, and out pops the equation with 2 V's, an A, and an X. And then 8th grade algebra. If you want to know what the time is, at this point we've got 2 V's, an X, and an A, and so you look at the list of equations and 2 V's and a T and an A, and I'm seeing this one right away. The definition of acceleration is 2 V's, an A, and a T. All you have to do is pick the right equation, and you can't go wrong from there. However, though, the next sort of problem-solving step above that incurs information that is not explicitly given. And so you need to be aware for some specific language here. If you are told that an object comes or starts at rest or comes to rest or ends at rest, you're being told a number without being given a numerical value. Obviously, anytime anything is at rest, its velocity is 0. And so oftentimes, if you start at rest or come to a stop, you're being told that one of your velocity values is 0, either v1 or v2. Another one that confuses people is this concept of maximum height. Real common, you throw something up, what is its maximum height? How long does it take to get its maximum height? What distance does it cover to achieve its maximum height? You are being given a number without being explicitly told so. Anytime an object is moving on the way up and achieves maximum height, you know that its final velocity is equal to 0. And then lastly, if you're told that something is dropped, you're being hinted at the fact that the initial velocity of an object is 0. When you drop it, you end up with a 0 value. And so this would be initial velocity is 0. And it can be sort of quite vague. If you're trying to identify 4 variables, here's an example. I take my marker and I drop it. How far does it go after 3 seconds? Well, I've only given you 1 variable. How are you supposed to pick a variable or an equation with 4 variables? And so you've got to step back and look at the problem. If you're dropping something, you're being told that the initial velocity is 0. If you are doing it in the atmosphere here on Earth, then you're ignoring air resistance and the acceleration is going to be negative 9.8. I said something like, how far has it gone in time equals 3 seconds? And so you're given a time. If you drop it, it starts at initial velocity 0. And you can also infer often that acceleration is negative 9.8 when things are moving freely. So in that case, I would be given a v. I would infer an a. I would be given a t, and I'm looking for an x. VATX, VATX. I look at the list and I go right to this, that x is equal to V1t plus 1/2 AT squared. It's a pretty good example of problem solving with the kinematics equations. Now let's look at some past problems. All right, this first question here looks like an old AP question. We've got an object released from rest. And so that means its initial velocity will be equal to 0. Got to remember that that's one of those examples where we're not given the value, but we have to infer it from what we read into. We're given the information that it falls freely for 3 meters in the first second. And so displacement is equal to -3. Now in all these kinematics equations, we have to be really honest about our vector quantities. A negative implies downward displacement. And then the time that it takes for that to happen is in 1 second. And the question here is, what is the magnitude of acceleration? And so what we have here is a v, an x, a t, and an a. And looking at my list of equations, I know that this is the relationship between these variables. Displacement, -3. Initial velocity, 0. Acceleration unknown. And time, 1 second. And solving that for A, bring the 2 over, -6, divide by 1. So our acceleration is -6. However, its magnitude, or just its size, is equal to 6. So the correct choice would be C. All right, next question. This looks like an IB question. A ball is tossed vertically upwards with a speed of 5. So it leaves, goes up, comes back down. We know that its launch velocity up is 5 meters per second. And the question is, how long does it take to return? So there's 2 ways to do this. You could take the time that it takes to go up and then multiply that by 2. Or you could just say that the change in velocity is that you start up at 5, and because the same time goes up and the same time goes down and it's the same acceleration, the change in velocity is from 5 to -5. And so that's the easiest in my perspective here. And so I have a V1 equal to 5, a V2 equal to -5, and I know this is on Earth, and so the acceleration is equal to -9.8. I'm looking for a time, and that allows me to take the definition of acceleration. And our change in velocity is approximately -10, and the acceleration is approximately -10, and that gives me a time of about 1 second. Correct answer would be B in that case. So here's a classic IB question. You've got an object initially at rest, traveling a distance d in a time t. And so we know that it's originally at rest, so we have a V1. We have a distance d and a time t, and we're told that it's a constant acceleration. There are no numbers in this. The question is just by which factor does one variable change when another one does. Classic IB stuff. So the relationship between these 3 variables is such: distance is equals to initial velocity times time, plus 1/2 acceleration times time. And the question is, what is the relationship between distance and time? And I can see here that one changes at a non-linear rate with the other. A small change in t will have a larger change in d because t is squared. So if you double t, the distance will change by a factor of 4. So this question is, if d is increased by a factor of 16, what happens to t? Well, the acceleration stays the same, and the initial velocity was 0, so we'll leave it. And so this question basically comes down to with this as a constant so it can be removed as well. How does t change to make d become 6 times bigger? Well, you might be able to see it in your mind, but if you have 1d and go to 16, basically the left-hand side's changed by a factor of 16. So the question is, by what factor does the right-hand side change? And if we do some math here, whoops, we'll see that the square root of 16 is equal to 4. And so the correct answer to this question would be C, 4t. So here's another interesting question. This is an IB question, and basically it proposes that an object falls on Earth, and the question is, how far does it move during its 4th second of motion? So there it is after its 1st second, and after its 2nd second, and after its 3rd, and after its 4th. The 4th second occurs with a displacement equal to this distance right here. So this is a hard one. We can't just directly put this in one of the kinematics equations. This is an example where I like to say, if you're not sure what to do, think of it graphically, and that adds another aspect for problem solving. And so if we were to look at a velocity time graph here, basically starting at 0 because it's at rest, and the velocity just increases at constant acceleration. And what I want to know is between the 3rd and the 4th second, how far does it go? And we know from our graphical analysis that how far it goes is the area in this given time. So we've got a triangle here and we've got a square. And we can identify what the values on the y-axis are so that we can do the math here if we can just figure out what the initial velocity of the object is at that moment in time. And so if an object falls for 3 seconds, its initial velocity is 0, what is its final velocity? Well, that is a v2 equals v1 plus at scenario. It's just acceleration times time. And we know that velocity is equal to acceleration times time, 9.8 times, in this case, it's been 3 seconds. So I'm going to approximate that to about negative 30. And if this velocity is negative 30, I think we can infer that the next velocity is going to be negative 40. And so we need to get the area of this right here. Well, it's 30 times 1. And the next one is 1/2 of 40 times 1. And that total is 50 meters. Now, 50 meters is not a choice, but I was abbreviating 9.8 to 10. And so it's no surprise that this answer is too large. There is an answer D that is 45, and so I'm going to take D for 45. Okay, final problem here. This is easy mathematically, but this will be difficult problem solving wise. This looks a little AP-ish. Basically, there's an object moving forward at constant velocity, and then it is given a negative acceleration for a certain amount of time. The time is actually pretty large, so it's going to move forward, and then it's going to slow down and come to a stop. And it either will time out before it comes to a stop, or if the time is long enough, it'll come back and move the other direction. And so our total question is where is the object after 11 seconds? So between time 0 and 1, so the first second, there's constant velocity. That velocity is 24 meters per second. And then we have a second phase of motion here. We're not really sure what's going to go down, but we know the initial velocity is going to be 24. And we know the acceleration is 6 in the negative direction. And we know that the time is equal to 11. And what we're after here is the final position. And so that is an x. The relationship between these variables is such there we go. And I'm going to use my calculator for this. 24 times 11. I'm going to use a minus there. Minus 0.5 times 6 times 11 squared. and that gives me the value of negative 99. And so basically negative 99 in this phase of motion, but it already went forward 24 here. So I've got to take 24 and negative 99 and put them together. I should get something like negative 75-ish. And I don't have a negative 75, but there is a positive 75. Let me reread the question. The body is given a constant acceleration. The negative, the position x of the body at 11 seconds is... I'm going to take negative 75 and call this a potential error in copying over.